Good day to you. We're here today at ESF's Hydrology and Hydraulics Laboratory, and we're going to be studying flows around objects today. And this is the device we're going to be using to do it. This is a flume, and we're going to be filling it up with water, and we're going to be putting things in it, and we're going to watch how flows go around those objects using a fluorescent dye. When an object interacts with a flowing fluid, there are two forces that need to be accounted for. One is the inertia of the fluid, and the other is its viscosity. When living things interact with flowing fluids, they come in a variety of sizes and shapes, and they can occur in one of two fluids, either air or water. And both of those things are going to impact upon the inertia and the viscosity of the interaction with the object. Now, this might seem to indicate that we have a lot of experimental work to do. If we want to look at flows over a leaf in air, for example, that might indicate that we have to take a leaf and we have to put it into a wind tunnel, and we have to measure how that leaf interacts with air. Fortunately, there's a tool at our disposal that lets us get around all that. It's called the Reynolds number, and the Reynolds number is simply the ratio of the inertial force over the viscous force. One of the beautiful things that the Reynolds number does for us is it enables us to look at a model or an object and put it in a convenient fluid, such as air rather than water, or water rather than air. And as long as we can get the flows and the interaction with the Reynolds numbers being the same, that is, with the same ratio of inertial to viscous forces, we can characterize flows of objects of any size and any shape and in any fluid. In calculating the Reynolds number, the first thing we need to do is to be able to measure the velocity of the flow. To measure velocity, we're going to use this bobber, plunk it in the water, and measure the time it takes to get from here to a point 2 meters down using this stopwatch. So here we go. That's the 0 point. And that took 15.7 seconds to go 2 meters. That works out to be about 0.13 meters per second. We're going to be looking at flows around a fairly simple shape today, namely a circular cross-section that's provided by this PVC pipe. We're going to be immersing the PVC pipe in the flume and looking at how water flows around that. Now, an important part of the Reynolds number is the diameter of this. And in this case, the diameter of this PVC pipe is 115 millimeters. And we can vary Reynolds number by putting in a pipe of a different diameter. And we're going to be using this narrow piece of PVC pipe. And that has a diameter of about 15 millimeters. This is about 1/10 the diameter of this. And this small pipe will give a Reynolds number about 1/10 the Reynolds number that we get with a large PVC pipe.
We're going to visualize flow using a stream of fluorescent dye, which fluoresces bright green under an ultraviolet light. Here we're injecting dye from a small tube positioned just upstream. You can clearly see the streamlines as the fluid flows around the large tube. You can also visualize the quite complex flows that result. Here we're dealing with Reynolds numbers up around 15,000 or so, which is the range where turbulent flows are quite common. Let's now look at these flows a bit more closely. Turbulent flow around the cylinder has three major components. At the cylinder's leading edge, there is a zone of relative stagnation as the upstream flow encounters the cylinder and is temporarily brought to rest there. As the water flows around the cylinder's lateral surface, the flow is laminar and smooth. Finally, just behind the cylinder's lateral face is a so-called zone of separation, where turbulent vortices are generated as the laminar flow just upstream separates from the cylinder as parcels of fluid in rotational motion. The separation occurs in part because the fluid behind the cylinder's trailing edge actually is moving in the opposite direction to the prevailing flow. When this retrograde flow encounters the prevailing flow, this imparts the rotational motion to the fluid, which separates as a vortex. The retrograde flow also produces a zone of relative stagnation behind the cylinder, seen in the accumulation of dye there. Now let's go to the smaller cylinder and lower Reynolds numbers to see what happens. With the smaller cylinder, we're dealing with Reynolds numbers on the order of about 2,000 or so. The wake behind the cylinder is still turbulent, but compared to the larger cylinder and the higher Reynolds numbers there, it is more orderly. Specifically, we see a phenomenon known as a vortex street, where turbulent vortices are shed first from one side of the cylinder, then the other. We also see vortices are retained behind the cylinder for a short time, then shed. If we drop the flow rate very low, we can bring Reynolds numbers down into the hundreds. There are still vortices being generated, but they now have an obviously laminar component to them. This means that viscous forces holding the flow together are now similar in magnitude to the inertial forces that initiate turbulence. It's even possible, with a few tricks with the flume, to drive Reynolds numbers for the small cylinder down into the tens and single digits. There is still a very slight rotational component to the flow, but the flow is definitively laminar, held together strongly by viscosity.
We saw at high Reynolds numbers that turbulent vortices are generated at the trailing edge of the cylinder. What we'd like to do now is to look at those flows near the surface a bit more closely. And to do that, we've rigged up a special device. It's a PVC pipe, just like we saw in the other video, or in the other segment. But instead, we now have a little port through here, drilled in the surface of the pipe, where we can eject fluorescent dye. And what we'll do is we'll put the pipe in the flume and we'll set it so that dye can be injected at the leading edge and rotate it around so that we can see how flows vary with the position of that port on the pipe.
Turbulence arises from the way pressure is distributed over a surface interacting with flow. According to the Bernoulli principle, pressure will be high and positive at the leading surface, but will fall to negative at the object's lateral and trailing surfaces. Negative pressures are particularly strong at the lateral surface. This imparts a complex flow in the same direction as the prevailing flow at the leading surface, but retrograde to the prevailing flow at the trailing surface. When the two flows meet, this imparts rotational momentum to a parcel of fluid. This is the origin of the turbulent vortex. Let's see if we can visualize these patterns of flow. When dye is released at the leading surface, we see it come momentarily to rest before it flows around the cylinder. The stagnation is evident also at the trailing surface. Note how the flow first is up and then down. This corresponds to the alternating generation of vortices that we see in a vortex street. At about 55 degrees upstream, flow over the cylinder is laminar and in the same direction as the prevailing flow. At about minus 30 degrees with respect to the prevailing flow, there is obvious retrograde flow from the back to the front of the cylinder. The separation zone is evident at about minus 40 degrees with respect to the prevailing flow. You can see the vortices lifting off the cylinder.
So what we've seen today is that when a fluid flows around an object, it flows around it in two very distinct ways. At low flow rates, you get nice smooth laminar flow over the surface of the object, but as you get to higher and higher speeds, that nice smooth laminar flow makes a transition to a more complicated turbulent flow. Now the transition from laminar flow to turbulent flow is tied in with the patterns of flow and pressure on the surface of this. Specifically along the leading edge of the pipe, the pressures are high, but they become negative up along the lateral part of the pipe. This means that there's going to be a forward flow right near the surface of the pipe along the trailing edge, and that imparts to the fluid flow the circular motion that is characteristic of turbulent flow. One of the other things that we found is that you can use the Reynolds number to actually model this process in a more general way. So for example, on the flume here, we looked at flows around a circular pipe in water. But we could just as very easily use what we found here to understand how air might flow around a circular pipe. So for example, here on the flume, we were looking at a water speed of about the 10th of a meter per second. That gave us Reynolds numbers on the order of about 15,000 for this particular pipe. Now if I had air in here rather than water, I would get the very same Reynolds numbers at a wind speed of about 2 meters per second. What this means is that the patterns of flow and the transitions to turbulence that you see would happen in the very same way at a wind speed of 2 meters per second as it happens in water at a water speed of about 0.1 meters per second. And so you can use this generality of analysis to answer all kinds of interesting questions, which we'll be looking at in more detail in another video. Well, that's all for today, and we will see you another time.